In this video, we're going to look at differences between weak acids and strong acids and how to calculate pH or even Ka for weak acids given different situations. So if you just remember the difference between a strong acid and a weak acid, strong is telling you how much it ionizes in solution. So a strong electrolyte, like a strong acid, is going to 100% ionize in solution. So if you're writing the dissociation or showing the breaking up of ions, you put one arrow to the right, showing that 100% is completely ionized. So if I put HCl in water, I don't find any H still bonded to a Cl. All I find is H pluses and Cl minuses separated. I don't find the HCl altogether as a molecule anymore. If I have a weak electrolyte, such as my weak acids, those are not going to 100% ionize. Actually, in most weak acids, most of it stays in the molecule form rather in the ion form. So if in this situation for acetic acid, for every 100 molecules of acetic acid, only 1% of it is going to essentially ionize into the acetate ion on H+. So usually 5% or less happens with weak acids, though it doesn't have to be. Okay, so even if we're thinking of this in a particle diagram view, here would be a strong electrolyte, like a strong acid or strong base, notice completely present as ions in water, whereas the weak acid or base is going to not be 100% ionized. A lot of it is still going to be in the molecule version, not the ion version. And this is really going to affect the pH. So a strong acid versus a weak acid, if you have the same concentration of acid put in solution, the strong acid is going to have more ions or more H pluses, so it's going to end up having a lower pH than the same concentration of a weak acid. You can achieve the same pH in a weak acid, it's just going to take a much higher concentration because not all of it is going to ionize. You're going to have to keep adding more to get into the same pH as a strong acid. If you have a pH of 3, though, that would indicate the exact same H plus concentration in both solutions. It's just you're going to end up having different concentrations to get to that pH of 3. So let's look at some examples. Remember your 6 strong acids: nitric, sulfuric, perchloric, or OMI, HCl, HBr, and HI. And what's great about strong acids, if they're asking about pH, is all you have to look at is the concentration of the acid, and that's going to give you the concentration of H plus in solution, because we know 100% of it, all of it is going to ionize. So something like, what's the pH of 0.04 molar perchloric acid solution? Okay. Perchloric acid is monoprotic, meaning there's one H plus for every one HClO4. So the H plus concentration is going to be equivalent to that of the perchloric acid solution's concentration. So my H plus concentration is just 0.04. So if I want the pH, all I have to do is take the negative log of 0.04. And I get 1.4. And you should again be aware of your of approximating how to get the pH in case you're on the AP for multiple choice questions. So it's helpful to turn your concentration into scientific notation. If you had 1 times 10 to the negative 2, then that exponent just becomes the pH. It would be 2. But if you have a coefficient other than 1, then your pH is going to be the exponent or 1 pH lower than that, somewhere between those values. So since my exponent is negative 2 and my coefficient is not 1, my pH is going to be between 1 and 2, and it is 1.4. The higher this number, the closer it would be to 2, and so forth. Okay, so, or the lower this number, excuse me, the closer to 2. So let's take a look at another problem. 2 molar hydrochloric acid solution. Okay, H plus is also 2 molar because HCl releases 1 H plus for every 1 HCl, and it 100% ionizes. And if I were to get the pH, I get negative 0.3. And my lesson here is just that it is possible to get a negative pH, and that will happen if you have an H plus concentration greater than 1 molar. Try it with your calculator, you will see. Okay, Strong bases are going to follow essentially the same rules because they 100% ionize. Make sure you memorize your strong bases. Group 1 and combustor, when joined with OH, are your strong bases. So if you have 0.028 molar NaOH, then my OH minus concentration is going to be 0.028 as well. And I can find the POH, which is just taking the negative log of OH. Anytime you see a little P in front, that means you're taking the negative log of that. And if you get your POH, just make sure that usually they ask you for pH in the problem, that you just make sure that you subtract from 14 to get your pH. And I get 12.45. Okay. If you would rather not use POH, you can use the KW to change the H plus into OH minus, to interchange H plus and OH minus. So since I have the OH minus concentration, I can find H plus and then do negative log of that, and I get the same answer. Okay. And just be aware with your bases, you have some dihydroxy bases. So for something like 0.001 molar solution of calcium hydroxide, in this situation, for every 1 calcium hydroxide, I get double the amount of OH minus. So I want to double my concentration of my original base to get my concentration of OH minus. And then I can find my POH by taking negative log of OH minus. And I can find my pH by doing 14 minus my POH, because pH and POH should add up to 14. Okay, and again, it might be helpful to have turned this into scientific notation so I can approximate what my pH is going to be between, or my POH is going to be between, for AP multiple choice questions. Okay. Now that you know about the pH of strong acids and strong bases, you can actually even apply this to a stoichiometry kind of problem, or really what turns out to be a neutralization or titration. So for this example, 200 milliliters of 2 molar NaOH is added to 500 milliliters of 1 molar HCl, and they want to know what is the pH going to be closest to. Well, we need to find out what's our reaction, and we need to find out, is one of these things limiting the reaction, because we have enough information to get moles of each reactant. So if I take the volume, change it into liters, and then I take the molarity and the volume in liters and multiply them together, I find that I get 0.4 moles of NaOH starting, and I have 0.5 moles of HCl. So what is it that they're reacting in? They're reacting in a 1-to-1 ratio in this neutralization. The acid plus the base gives me water plus the salt. So which one is limiting my reaction? Am I going to have one of them in excess? Yeah, my NaOH would be limiting the reaction. That's going to be completely used up, and I'm going to have some HCl left over. How much HCl am I going to have left over? Well, 0.4 of it would react with the NaOH, so I'm going to have 0.1 of it remaining. So even though my products here are neutral, H2O is neutral, NaCl is a neutral salt, I'm going to have 0.1 moles of HCl left in solution, which is going to contribute some H plus ion, which is going to affect the pH and make it not neutral. It's not going to end up being 7. So in order to find the pH, remember pH is negative log concentration of H plus, so let's change moles of HCl into concentration of HCl, which is really the same thing as concentration of H plus, because this is a strong acid, it 100% ionizes, and it's monoprotic. So my H plus concentration would be 0.1 moles, and my volume, when I mix these two together, would be 700 milliliters, so I would divide that by 0.7, okay? And I get about 0.1 molar, exactly it would be 0.14 molar if I have my calculator available. And so doing the negative log of that, I would get 0.848, or if I don't have my calculator available, the pH should be somewhere around 1. so my answer would be A. So you can actually find the pH given any neutralization reaction like this, especially if you have your strong acid, strong base components. Now the question becomes, well, how would a weak acid be different? And a weak acid, remember, does not 100% ionize. It is going to only a fraction of it typically is going to ionize. Most of it's going to be left in its molecule form. So we're going to always indicate these ionizations with a double arrow to indicate this is an equilibrium condition. And when we have an equilibrium condition, what are we usually going to end up making? We're going to end up making ice boxes to solve the problem. But anyway, if we have an equilibrium situation, we can always find K, the equilibrium constant, by doing products raised to their power, that is their coefficient, over the reactant raised to the power, that is the coefficient. Remember not to include solids or liquids, but everything here is aqueous. And because this is so common of a situation, rather than calling this Kc, we're going to call it Ka. And this is actually in your AP Chemistry formula sheet. The greater the value of Ka, the stronger the acid and the greater the tendency to ionize. So you can look up in your textbook in the appendix, there's a bunch of different Ka values for different acids. The larger the Ka, the more ions you have in solution, so the stronger the acid. Just like if you remember KSP for your ionic compounds, the higher the KSP, the more ions you had in solution. Very similar judge of number of ions. Strong acids tend to have Ks that are much greater than 1. So if you kind of look at this, HI is a strong acid, has a large Ka, HBr, very large Ka, and your weak acids will typically have Kas that are less than 1. Okay, and again, just as a reminder, make sure that if you're looking at which H is coming off of your weak acid, that typically it's the H that's connected to something that's pretty electronegative, an N, an O, an F. Typically not an H that's connected to C's, one exception being hydrocyanic acid. So a lot of problems with weak acids you see will either ask you to calculate the pH given the Ka, or we'll ask you to calculate the Ka given the pH. And this is actually going to be really similar to equilibrium problems that we've seen back in chapter 13 or back when you did equilibrium problems. The thing to remember is whenever you see a weak acid, it's going to represent an equilibrium condition. pH is always going to be the H plus that's present at equilibrium. And again, typically you're going to need to do an ice box. Let's look at an example. I'm going to look at how to calculate Ka from the pH. So this problem is telling you the pH of a 0.1 molar solution of formic acid at 25 degrees is 2.38. And again, most of the time you're going to be at 25 degrees Celsius because we know the value of Kw at 25 degrees Celsius. Calculate Ka for formic acid at this temperature. So let's just write the ionization equation. If I look at this, this is an acid. It has a carboxyl group. Okay, which H is the one that's ionizing? It's the one that's attached to this O, not the one attached to the C. So that's the one I'm going to remove in my reaction, just to make sure, in case there's questions about it structurally, it would be helpful to just make sure we're removing the right one. This is a weak acid, so when I write the ionization equation, I want to put double arrows because not 100% of it is going to ionize. Okay. Now I can write a Ka. Okay. Eventually, I'm probably going to be plugging into this to solve for the Ka that they're asking me for, but I need the concentration of all of these things at equilibrium. So how can I go about doing this? They give me the initial pH of formic acid, and they give me the pH. And when I look at the pH, that's essentially giving me the H plus concentration at equilibrium. Okay, so from the pH, you can always find the equilibrium concentration of H plus. Make sure you're comfortable plugging into pH and solving for H plus. Essentially, to solve for H plus, you're taking 10 to the each side to get rid of that log. So if I use the pH of 2.38, I find that the H plus concentration is 4.2 times 10 to the negative third molar. Okay, this is the H plus at equilibrium. So now let's go into an icebox, which is typically going to be something that you make for equilibrium problems. And they gave me the initial amount of acid, so it makes sense that I want to do an icebox, which has an initial column or initial row. So initially they give me the formic acid, and what can I assume about my products if they don't give me values initially? I can assume 0. Okay, my change is coming from my stoichiometry, so minus, I'm going to denote for reactants because typically they get used up. Products get made. If there was a coefficient of 2, I'd put a 2 there, but I don't have any coefficients here. And now I know my equilibrium concentration of H+. I got that from my pH. Yay, I have a column that is completely solved for. So if you have a column that is completely full, you just use that to solve for x. Okay, so I'm just reading this down as an equation. 0 plus x equals 4.2 times 10 to the negative 3. So now I can put in or solve for my other equilibrium columns now that I know my x. Okay, so this one, 0 plus x, if x is just 4.2 times 10 to the negative 3, so is this one. And this would be 0.1 minus 4.2 times 10 to the negative 3, which is still about equal to 0.1. Notice subtracting this really, really small value is really not going to do much to the 0.10 if I'm keeping sig figs. And that is an important thing to keep in mind that we're going to look at later when we look at the 5% rule. Notice if x is really, really small, if not a lot of this is ionizing, then my initial concentration of my weak acid is really not going to change much by equilibrium. Okay, now I have all my equilibrium values. I can plug into my Ka expression and solve for what Ka is. Okay, and I get 1.8 times 10 to the negative 4, which makes sense. If this is a weak acid, it should be something that's typically less than 1. Another indicator of a weak acid, or the strength of a weak acid, just like how there's Ka, the higher the Ka, the stronger the acid, the more it ionizes, is something called percent ionization. This is not in your formula sheet, so it's an equation that you should know when you're sitting for the AP. Percent ionization is your H plus concentration at equilibrium over your initial concentration of acid, and then just times 100 to turn it into a percent rather than a decimal. And this kind of makes sense. How much of your initial acid is ionizing into H plus by the time you reach equilibrium? So in this past example, I can actually calculate it. Our H plus at equilibrium we found to be 4.2 times 10 to the negative third. Our initial acid was 0.1, so if I just take those two numbers and divide, I get 4.2%. Okay, a lot of acids you're going to get 5% or less, and we're going to end up coming up with a rule for that. Okay, take a moment, look at this example, maybe pause the video and give this example a shot. Okay, let's go through the answer quickly. Okay, again, I find it helpful to write an ionization equation first to start off. It's this H, one of these, this H that's connected to one of the O's that's ionizing, not one of the H's connected to the C, because you want the H to be connected to something that's more electronegative, so that that electronegative atom holds onto the electrons, and you can easily lose your H as an H+. We call that an ionizable H. You have your double arrows to indicate equilibrium. Okay, I can write a Ka expression to start with, or I can go straight to an ice table or an ice box. I know my pH, that's going to give me the H plus at equilibrium for my ice box. Okay, and I should find that my H plus is 1.3 times 10 to the negative 5 molar at equilibrium. Notice it's a very small value. Not a lot of this is ionizing because it's a weak acid. Okay. I could put in my initial acid. Okay, I can assume that my initial ions would be 0 if it's just put into solution. Minus x for my reactants, plus x for my products, plus putting in any coefficients that are there. I don't have any. And here's my H plus concentration. Let's use this column to solve for x. X is just 1.32 times 10 to the negative fifth. So then that means this box is also 1.32 times 10 to the negative fifth. That's the concentration of this ion at equilibrium. And if I do 0.2 minus 1.32 times 10 to the negative fifth, which is 0.0000132, it's really not going to have much effect on this number at all. If I'm holding sig figs, this is still going to be 0.2. So notice my weak acid concentration is really not going to change much by the time I get to equilibrium. I can find my Ka by plugging in, and I get 8.71 times 10 to the negative 10, which is smaller than last time. It makes sense. I have a much smaller H plus than last time as well. And I can find my percent ionization by plugging into the equation, putting H plus concentration from equilibrium on top, which I got from pH, and putting my initial acid on the bottom, and I get 0.0066%, much weaker acid. You can go in the other direction. Instead of calculating Ka, they might give you the Ka and ask for the pH. So if I look at this problem, calculate the pH of a 0.3 molar solution of acetic acid at 25 degrees, and I give you the Ka. Now just a quick question, how would this problem be different if this were a strong acid? Or how would you approach this problem if it were a strong acid? If it were a strong acid, I wouldn't even need a Ka. It would not be an equilibrium condition. All I would have to do is take my concentration of the acid and turn that into concentration of H plus, because 100% of it would ionize, and then I can do negative log of that and get the pH. It would be a much simpler problem. But this is a weak acid. 100% does not ionize. So I cannot just turn this concentration into the concentration of H plus. I'm going to end up using an icebox to solve for its concentration at equilibrium. Okay, so again, I find it helpful to write an ionization reaction. It is this H that would be ionizing since it's connected to a more electronegative O. It's an equilibrium situation. So I can eventually use this Ka to solve for one of these unknown concentrations if needed. They give me an initial amount of acetic acid, so what should I end up making? Oh, let's make an icebox. So if I make an icebox, initially I know the acid. I can say I have 0 of each ion to start with. We'll put our changes in. And in the problem, do they give me any information about equilibrium? They don't give me pH, so I don't know the H plus at equilibrium. So what do I do if I don't know things at equilibrium? Well, let's just fill in these boxes in terms of X. Okay, so this would be 0.3 minus X, this would be X, and this would be X. But what did we learn from the last values, the last problems? What do you think I can estimate this box here to be? Rather than 0.3 minus X, how do you think X is going to compare to 0.3? Do you think it's really going to change its value much? So what we can do is we can do this assumption. We can assume that X is very, very small. We can assume that Ka is small for this weak acid. And we can assume that when I subtract X from 0.3, that it's really not going to change the value much. So I can assume that 0.3 minus X is really just going to be 0.3. This is actually called the 5% rule, because in order for this to happen and to be a valid argument, when you find the percent ionization, it should be 5% or less. And we're going to look at that after we do this problem. So why that's important is because by doing this assumption, I am not going to have a quadratic equation anymore. I'm not going to have to worry about the solver in my calculator or plugging into the quadratic formula. I'm going to get a much easier problem to solve. So now, if I plug these into my Ka expression, here's my Ka from my problem. X times X gives me X squared on top over 0.3. If this was 0.3 minus X, I would have a quadratic formula to solve, which would be a lot more time consuming, especially for the AP exam. So this is a really, really good assumption to make sure you understand and can practice and can use. Okay, most of the problems on the AP you're going to be able to use this assumption. So now it's just algebra solving. Okay, I multiply these, cross multiply, I get x squared equals 5.4 times 10 to the negative 6. Take the square root of both sides, and I get 2.3 times 10 to the negative third. Okay, make sure you answer the question, the initial question. So that's my concentration of H plus and also my concentration of acetate at equilibrium. Is that what it asked me for? It asked me for pH. So let's just make sure that we now get the pH. How do I get the pH? I take the negative log of the H plus concentration. So if I take the negative log of that, I get a pH of 2.64, which makes sense for an acid. If you got a pH higher than 7, I would say maybe recheck your work. Okay, now because we use that assumption, which I said is called the 5% rule, we should find the percent ionization and make sure it's 5% or less. So remember, percent ionization is the H plus at equilibrium over the initial acid times 100, and if I do that, I get 0.77%. Technically, if you get more than 5%, you should redo the problem without that assumption. Though even if it's more than 5%, it really doesn't affect the answer all that much. Just showing you how it would be redone without the assumption. If I had 0.30 minus x, it turns into a quadratic formula, and I would have to solve for x with the quadratic equation or with solver or with graphing or something like that. But look, my answer is exactly the same. Okay, so when to use the 5%? The 5% rule usually works if your value of K, so in this case it's an acid, so your Ka is 10 to the 3 smaller, 1,000 times smaller than the value of the known initial concentration, then this will work. Okay, because obviously percent ionization is something you're doing at the end of the problem. You want to know starting the problem, should I use it? Another time I find that it's helpful to work is if your K is in the 10 to the negative 5 scale or lower. That's a little bit less, a little more dicey to use as when to use it. I would definitely use this first condition. So if your K is 1,000 times smaller than your initial concentration, then you can use it. Okay, and now that you know how to do this assumption, you can actually use this assumption on any equilibrium problem. So you can use this on Ka's. When you get to weak bases, you can use it on Kb's. You could go back and use this on any KSP or Kc problem. If your K is 10 to the third, 1,000 times smaller than your known initial, you can use it. Or again, if your K is 10 to the negative 5 or less, you can usually use it too. Okay. Also, now that we can use this assumption, anytime you're using this assumption, you're going to get down to this kind of shortcut equation that you can use, which is really nice to use for multiple choice, even nice to use for free response. Your H plus concentration is going to be found by taking the square root of your Ka times your initial acid concentration. And we're going to look at why you can use this. And this equation is not on your formula sheet. So if you're going to use it, it's something you'd have to know or memorize or understand. So let's look at this problem one more time that we just did, but I'm going to retry it with the shortcut, and let's see if we get the same answer. Okay, so as long as it's a monoprotic weak acid, okay, and I can use that 5% rule, let's see. Okay, here's my Ka. Here's my initial concentration. The difference between them is 10 to the third or greater, so I can use that shortcut. I can also use that assumption according to that condition we just talked about. So if I plug in H plus, okay, equals, here's my Ka, here's my initial acid, taking the square root, and oh, there's my H plus, okay, and here's my pH. Same exact numbers, much quicker to do rather than doing an icebox. Again, the reason why you can do this is because given this is really just your Ka rearranged to solve for H plus. And let's look at another example, and I'll show you again how this kind of works out in the answers. But I want you to take a moment, maybe pause the video, try doing this example both with an icebox and also with a shortcut. And when you're doing the icebox, see, can you use that assumption, that 5% rule? Okay, so going through this, again, I find it helpful to write your ionization equation for your acid. Here's the equilibrium condition. In this case, the H that comes off is connected to the C. It is the only H in your acid. And here's my Ka, and I know my Ka value, but I'm going to have to solve for the H plus concentration so I can get the pH. So they give me initial stuff. Let's start with an ice box. Okay, here's my point 2. Assume 0, 0. Put in my changes. I don't know anything at equilibrium, so I'm going to put in everything in terms of x. But I'm going to assume x is very small, much smaller than 0.2. If I go back to the original problem, my Ka is 10 to the negative 10, and this is on a scale of 10 to the negative 1, so I have much greater than a 10 to the third difference, so I can definitely use that 5% rule. So I'm going to make this just 0.2, make this x and x, and if I plug into Ka, okay, I get 4.9 times 10 to the negative 10 over x squared times x squared equals x squared over 0.2. Hey, wait a minute. When I rearrange this and take the square root, you're going to end up seeing, hey, wait a minute, that is the shortcut that I just said to remember, right? That H plus concentration is going to be the square root of the initial acid times the Ka, right? And that's what we were just doing here. That's why that shortcut works. It's being derived from your ice box, essentially, and it's being derived from your Ka. These two things being equal, as long as it's a monoprotic acid, that's where you get the square root from. That I could have just plugged right into instead of doing the ice box. Again, you can only use that for a monoprotic weak acid, and you can only use it if you can follow that 5% rule. You can use that assumption. Okay, so I could have just plugged right in and get that same H plus concentration. Now just make sure you're answering the question. They don't ask for H plus, they ask for pH and percent ionization. So let's make sure we do that with the H plus we just found. I should get a pH of 5, taking the negative log of the H plus. And for my 5%, I should more than qualify for the 5% rule, doing my H plus over my initial acid. I get 0.005% ionization. So hopefully this 5% rule assumption, and even maybe that shortcut equation, if you want to go straight to that, can make problems easier and faster, especially if they're multiple choice. And you can use it in free response as well. Just remember what monoprotic means is that you have one ionizable H plus, something like HCl. You might have situations where you're dealing with polyprotic acid, meaning more than one H plus is being donated, whether in the situation of a diprotic acid or a triprotic acid. And there's actually shortcuts for handling some of those as well. So a polyprotic acid has more than one acidic proton, more than one H plus that's being lost as an ion. And these actually ionize in different steps with different H pluses, different Ka values. So something like H2SO3, sulfuric acid, there's two H's that can actually be lost as H plus, and it would happen in 2 steps. And we give a Ka to each step. So you might see Ka1 and Ka2. If there were 3 as H pluses to be released, you would see Ka3. So they are given numbers after the A. Okay, so they refer to which proton is actually ionizing. And what you'll always notice is that the first proton is always going to be easiest to remove. Your first Ka is always going to be the largest, indicating the most ionization. The Ka value is going to start to decrease with each proton removed, meaning less and less of it, less and less of those ions are going to be present in solution. It's going to be harder and harder to remove that H plus. Now there's a general rule that you can use for problems for polyprotic acids, and it's going to be very similar to that 5% rule conditions. So if you remember, what was that difference you were looking for between the initial acid and the Ka? What was that magic number? 10 to the 3, right? Or 1,000-fold difference. So for polyprotic acids, you're going to have a similar condition. Whereas if the difference between the Ka values from the first ionization or the first dissociation and the subsequent Kas is 10 to the third or more, then the pH is only going to depend on the first ionization. So something, if I'm looking at like this ascorbic acid, here's my Ka1, it's on a 10 to the third scale. My Ka2 is on 10 to the negative 12th scale. Do these differ by 10 to the third or more? Yeah, they do. So what I can do for a problem involving ascorbic acid is I can just treat it as a monoprotic acid. I can just treat it with a monoprotic acid and make the Ka 10 to the 8 times 10 to the negative third, and it becomes just like any other weak acid problem. And that's what most of the polyprotic acid problems you're going to deal with are going to do. So for instance, let's look at this example. What's the pH of a 0.0037 molar solution of H2CO3? Is that a strong acid? Nope, that's a weak acid. If I go back here, I have my Ka1s and my Ka2. I'm just going to write them down here. Here's my Ka1 and here's my Ka2. Check if they differ by a factor of 10 to the third or greater. Do they? Yeah, they do. So all I have to do is treat this as a monoprotic acid, monoprotic weak acid problem like I did before. Okay, and can I use that 5% rule assumption if my Ka is 10 to the negative 7 and my initial pH is 10 to the negative third scale? Yeah, that differs by 10 to the third or greater as well. So really the only ionization I'm looking at is the first ionization, and the only Ka I'm going to use is that first Ka. I'm going to treat it like any other problem. I can do an icebox where I have my initial. Okay, I'm going to use my 5% rule that I just said I can use, so that first box just becomes 0.0037, and I get X and X, and I can plug into my Ka, and hey, wait a minute, I could have used that shortcut, right? Now I'm treating it as a monoprotic weak acid that has that 5% rule. I could have plugged right in and solved for H plus with using that square root of Ka times the initial acid concentration if I wanted. Okay, but either way, once I have my H plus, then I can find my pH. I can also find my percent ionization, and I get 1.1. Hey, that 5% rule worked. Okay. So these are a lot of different weak acid problems, and again, these should look really familiar to things you've seen in equilibrium problems. Just remember, if you see strong acid, not an equilibrium problem, weak acid, equilibrium problem. Strong acids and weak acids, they can achieve the same pH, but it's going to take different concentrations. You're going to have a lot more, you need a lot more higher concentration of your weak acid to reach the same pH. But if you are at the same pH, like a pH of 2, then your H plus concentration is the same in both solutions, even if one's a weak and one's a strong acid.